Yeah. Good morning to all. Pavan Chandra, can you able to see the presentation?
Yes, sir.
Just read the first line. Only the first line.
Measure of information.
Yeah.
Consider
Okay.
the
Very good. Thank
communication
you.
system.
Yeah. Okay. Okay. Thank you. Thank you very much. So in today's class, in Unit One, we are going to see the basics of information. So the first basic is about measure of information. So consider your communication system that transmits messages with sequences M1, M2, M3 till Mn, having the probability of occurrences with for message M1 as P1, for M2 P2, for M3 P3, till if you have Mn, it will be till Pn. So how do I measure this amount of information? Is that by simply calculating the amount of information. So the amount of information transmitted through the message sequences till mk, instead of I'm writing it as mk, and with the probabilities of maximum pk. So then the equation can be written as amount of information which I represent for I with the maximum k resemblances will be always equal to log to the base 2 1 divided by pk. So this is your equation for measuring the information in any communication system. So next we have some properties for this information to be measured. So if there is more uncertainty about the message having the information, then the information carried will also be present. Okay. If there is more uncertainty about the message information, the information also can be carried out. This is the first property. Second property is that if the receiver knows the message, whatever is being transmitted, then the amount of information carried will be always zero. This is your second property. The third property is that if I consider two messages, one with message M1 having information I1, another one message M2 having information I2, if there are two such things, so the total amount of information carried due to this M1 and M2 will be always the summation of them. So the amount of information will be I1, I1 plus I2. So where I1 is the information carried by message M1 and I2 is the message carried by message M2. Okay, so these are your properties. So next, coming to the next information, the basic terminology is about entropy. Okay, so next terminology is about next terminology is about entropy. Entropy is a simple that it is an average information that we had seen now. Okay, average information. So the average information is being a collective information of the existing information that we had seen. So consider that we are having m different messages with probabilities m1, m2, m3 till mm. So this is mm. I will overwrite it. It is m m mm with m different messages and having the probabilities of occurrences with p1 for m1, p2 for m2, p3 for m3 till pm for mm. So then the probabilities will be P1L for M1 message being transmitted, P2L for M2 being transmitted, P3L for M3 being transmitted till PML for MM to be transmitted. So this is your average information. So how do I calculate this? I'll show you in the next. Okay. So this is how to find the average information. So if I take instance for I1, so the equation will become log to the base 2 1 divided by P1. Okay. Since there are P1L number of messages of M1 being transmitted, so the total information due to all the message will become I1 total is equal to P1 L log to the base 2 1 divided by P1. And this is for M1, right? For M1. And for M2, due to M2, it will be I2 total information total is equal to probability of the occurrence P2 into L log to the base 2 of 1 divided by P2. So this is how do we find entropy. Okay. So next is the properties. So there are two properties for entropy. One is if the event is having a P of k as 0 or 1. If P of k is 0 or 1, then the entropy is 0. Entropy is represented by capital H. I'll write it. I think this is not visible yellow. I'll write it in red. H. H. So if the event of occurrence of P of k is equal to is either 0 or 1, so then entropy will be 0. And when the occurrence of P of k is 1 divided by M for all the M symbols, then they are always equally likely. So this is your second property of entropy. So next basic terminology or the basics of information is your information rate. So information rate is represented as R, capital R, which is equal to small r into H. So already we are familiar with H. H is your entropy. H is your entropy. Capital R is your information rate. Small r is the rate at which the messages are being generated. So in general, the equation can be written in terms of information rate R is equal to information rate, which is messages per second, into entropy, which is information per bits. So you can easily find the unit for information rate, which is information bits per second. So which is information rate R is represented in as average number of bits of information per second. So this is a definition of information rate. So these things, discrete information, stationary sources, all this are the basics that we will see in unit number 2. All this comes in unit number 2. So I'll keep this slide aside and we'll go for another topic in this. The basics of information in unit 1. I had given it as consolidated in a single Jamboard. So whenever we go for unit number 2, there we will see the mutual information and the other basics of discrete memoryless sources, discrete information sources, and the average source informations. Okay. So coming to the next topic, which is your source coding theorem.
Zoom
source
it, sir.
coding theorem.
Can you magnify it?
Yeah. I'm doing the same. Is this visible now? Now is it visible?
No, sir.
Now check it. This
Okay, sir. Okay, sir.
now it's okay. 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 So this source coding theorem was given by Shannon. It is considered to be as the first theorem as postulated by him. This is an efficient source encoder which is used for converting your signals into codings, which should satisfy the following conditions. Okay, so the first condition is that code words code words generated by the encoder should be binary in nature always. It resembles that it is zeros and ones. And the source coder should be always unique in nature. So which is your second. So when you go for unique in nature, we need to see whether it is an uniquely decodable codes or not. So that represents that the every code should represent an unique message. Every code word should represent an unique message. So that should be satisfied. So if you want to step into the source coding theorem, we should be familiar with the prefix codes. We should be familiar with the uniquely decodable codes and the instantaneous codes. Okay. So don't worry, everything we'll see in detail when you solve a problem on that. It's very easier. So this is your theorem. The theorem states that with a discrete memoryless source, of entropy h, the average code word length for any distortionless source is bounded by this equation, which is the average code word length greater than or equal to entropy h. So this is your theorem stating always for a discrete memoryless source, the entropy with an entropy h and an average code word length n is bounded that the average code word length n is always greater than or equal to h, which is your entropy. So entropy is your average number of bits. So when you expand the relation, so n is the average number of bits in the code word. So we know that entropy h is what? So n is equal to summation k is equal to 0 to l minus 1 pk nk. So where k represents the maximum number of bits, l represents the number of messages emitted by the sources, pk is the probability of the last message or the kth message, and nk represents the number of bits assigned to each message. So this is an important coding theorem. Next, computing efficiency of a source encoder. The efficiency of the source encoder can be computed by taking the ratio between the entropy and the average. Okay, h by n bar. Next is to find code redundancy. Code redundancy is the measure of redundancy bits. So I forgot here n, so kindly include n here. N should come. Redundancy. Redundancy bits. So measure of redundancy bits in the encoded message sequence is your code redundancy. And we have a formula for that, which is 1 minus code efficiency. So whatever the efficiency that we obtain here, so 1 minus of that, we get redundancy. Redundancy is the number of errors or number of bits being error that we can find it easily. So next is your code variance. So code variance is sigma square, which is equal to summation k is equal to 0 to l minus 1 pk nk minus n bar. So n bar is your average number of bits. that we are familiar. And this variance is a measure of variability in code word lengths. So this is your next terminology in source coding theorem. So after the source coding theorem, we will see decoding algorithms. So there are two decoding algorithms. One is Shannon-Fanon decoding algorithm. Second one is Huffman decoding algorithm. Everything I'll explain you with a problem so that you can understand betterly. So I'll start with just the introduction to this Shannon-Fanon decoding algorithm, or the Shannon-Fanon method, or the Shannon-Fanon coding technology. So Shannon-Fanon, the probabilities of occurrence of all the messages are not equally likely. If so, then the entropy gets reduced, which in turn also reduces the information rate. So this is your natural occurrence. The probabilities of occurrence of all the messages, they are not equally likely, then entropy gets reduced, information rate also gets reduced. So for this purpose, Shannon and Fanon algorithm is used to encode the messages depending upon their probabilities, such that more information rate can be transmitted. So how does it does is that the algorithm allots less number of bits for highly probable messages and more number of bits for rarely occurring messages. So this you will be able to see in the problem that we are going to solve. Need not worry. Okay. So now it starts the basic now. Consider a problem one. So let me check how many are present such that the others also. Okay, so approximately 16 are present. So maximum strength is obtained, I think so. So if you're having a paper or a pen or if you're having a book, kindly make a note of this question. This is an important concept of how to solve the Shannon-Fanon coding and even Huffman coding also. Okay. If you're having, make a note, or else I'll share all these things later. But if you do parallel in practice, it may be useful for you. So first of all, let us see what is the question is. The question is for a discrete memoryless source X. There are they are given that there are six symbols, varying from x1, x2, x3 till xx. To make sure six symbols are being given or not. For this, we need to calculate entropy, we need to calculate average length, we need to calculate efficiency, we need to calculate redundancy. So there are four parts to be determined for this problem. One is entropy, another one is average length, another one efficiency, another one redundancy. So these are the given values. So Px1, probability of x1 is 0.3, probability of x2 is 0.25, probability of x3 is 0.2, probability of x4 is 0.12, probability of x5 is in 0.08, probability of x6 is 0.05. So this is your given question. Okay. So how do we solve this? So first I'll take a method called Shannon-Fanon encoding method to solve this problem. Okay. So first thing is to find entropy. Just a minute, I will show you. First thing is to find entropy. So what is the formula for entropy? We all are familiar with. solution to this problem is to find entropy first thing. So how do I find entropy? Entropy formula is summation k is equal to 1 to m pk log to the base 2 1 divided by pk. So since we have 6 messages in the question, so our values will vary from k is equal to 1 to 6, and our probabilities of measurement will vary from p1, p2, p3 till p6, since there are 6 messages. So on substituting m value, on substituting k value from 1 to 6 messages, we get p1, p2, p3 till p6. So substitute in the entropy formula. So what is this p1 value? Just go back and see. What is p1 value? P1 value is the probability of occurrences of first symbol, so which is x1,
0.3.
which is 0.3. 0.3 is p1, and log to the base 2 1 divided by 0.3. So next is p2. So for p2 the occurrence is 0.25. So p2 we can write 0.25 log to the base 2 1 divided by 0.25, and so on till all the 6 symbols that you're writing. So probability values, you should refer the question. Okay. So on using your calculator, use your calculator appropriately and check whether you're getting this value. For 0.3 to log to the base to 1 divided by 0.3, you'll get this 0.521. For 0.25 log to the base to 1 divided by 0.25, you'll get 0.5. For 0.2 log to the base to 1 divided by 0.2, you'll get 0.4643. And for 0.12 log to the base 2 1 divided by 0.12, you'll get 0.367. And for 0.08 log to the base 2 1 divided by 0.08, you'll get 0.291. And similarly for that, 0.05 log to the base 2 1 divided by 0.05, you'll get 0.216. So make summation of all these things. You'll get H value, which is entropy. So entropy, when you make adding of all these 6, you'll get 2.3568 bits per message. So this is your common thing, common formula for finding entropy, either in the case of Huffman or in the case of Shannon-Fenner also. Okay, is this clear? I'll go to the next. Our next is to find code word length using Shannon-Fenner coding. Using a Shannon-Fenner coding. So what does it gives us? Or what we are going to do using the Shannon-Fenner is that, in order to obtain the code words using Shannon-Fenner coding, we should have an idea about what is the procedure for that. Okay, so the procedure is so simple. First one, partition is made such that sum of probabilities in both the partitions are almost equal. Second, messages in the upper partition are assigned bit 0 and the lower partition is assigned bit 1. And The partition is continued till there is only one message in the partition. So from this, what we get is that as the probabilities of messages decreases, bits code word also increases. This you will be able to understand in a better way when we see the same in this. So first, write the occurrences of symbols in the given question with respect to its probability as in this. So Shannon-Fanon algorithm, I'm writing my title. I'm separating into two columns. One is the symbols. So let me check the symbols first. What are the symbols being given? It's given as x1, x2, x3, x4, x5, xx with values 0.3, 0.25, 0.2, 0.12, 0.08, 0.05. Okay, so this is a given question. So write them in descending order. So that is the first information about Shannon phenomenon. So whatever the values of symbols of occurrences of x1, x2, x3, x4, x5, xx are given, write them in descending order. So check this whether they are in descending order regardless of the question. In question they will give in descending order. If not so, if they don't give in descending order also, we should write it in descending order. So you can see that 0.3 is higher than 0.25 and this is higher than 0.2, this is higher than 0.12, this is higher than 0.05 and this is higher than 0.05. So everything should be written in descending order. The probability of occurrences in descending order. So this is the first step to be done. Any doubts? Okay. I'll go for the stage 1. Do not see the other stage 2, stage 3 and stage 4. Just concentrate on stage 1 that I'm showing you. I'll explain one by one. No issues. Stage 1. Is stage 1 visible? Okay. Now is the case of partitioning. So how do I partition in stage 1? So what is the condition in partitioning is that we should partition the given set of symbols with equal probabilities. With equal probabilities. So for example, if I partition, if I add these two probability, for example, you add these two probability, what do you get? We get 0.55. And I divide this whole probability into 2 and I add these two, I get 0.55. Now I add these two and see how much you get. We get 0.45. Okay, so instead of this, somebody will be having a doubt, so I'll make it that. For example, I add first 3 in red color. So I add first 3, what will I get? I'll be getting 0.3, 0.55, 0. I'll get 0.75. So the remaining would be this 3. So these 3, what do you get? 0.2, 0.25. So now tell me, if I take 0.75 and 0.25, whether they are equally probable? Anyone can turn on your mic and tell me whether 0.75 in one side and 0.25 on the other side are equally probable. No answers. Anybody can tell me. No. So yes. As you said, they are not equally probable. So what is equally probable is that if I add the first two, I'll just erase. If I add the first two, I'll be getting 0.5, and if I add the remaining, I'll be getting 0. So I'm erasing the red color. I'll be getting, if I add the first two, I'll be getting 0.55. If I add the remaining, I'll be getting 0.45. So where are those are equally probable. So equally probable in the sense more or less equal to each other. Whereas when you see the first three, it gives you 0.75. The remaining three, it gives you 0.25, which are more or less not equally probable. So I consider only these two. So for this 0.55 is your added probability. For this it is 0.45. So since it is divided into two parts, the upper half assign zeros, lower half assign ones. So since there are two probabilities assigned, 0 for 0.3 and 0 for 0.25. So the remaining for x3, x4, xy, xx, 1, 1, 1, 1. So this is your stage 1 computation. Any doubt in this? Any doubts? Three parts. Yeah, if you do three parts, what happens? The probability is that for these three, we got 0.75. For these three, we got 0.25, which are not equally probable. In the sense, they are not more or less equal to each other. So whereas when you compare these two, they are equal to each other. And I think you are asking three parts, dividing into three. No, dividing into three is not our binary format. Dividing it into two parts, zeros and ones, is our Shannon-Fennon coding since it deals with binary. I think the second answer is your question, correct? Chikala, what you asked, I had answered. We cannot divide into three parts because we are dealing with the zeros and ones, so which gives only two representation. So according to the Shannon-Fennon, it is applicable only for binary. Yes, tell me, Chikala. So shall we proceed for the next stage?
Yes, sir.
Okay. So next stage is stage 2. So in stage 2, stage 1 remain will as same. Stage 1 will remain same. So I'll draw a line. So till this, till the red, it is same. Now we are going to do only this stage 2. In stage 2, the same procedure we are going to repeat it for each and every blocks. So this will become x1, x2 will become block 1, x3, x4, x5 will become block 2. So first we shall see for block 1. So divide this into 2 with equal probabilities. So here we get 0.3, here we get 0.25. So upper half 0, lower half 1. So this will be over in stage 2. And we have another block which is block 2, which has 4. So out of these 4, find equal probabilities. So where do you have equal probabilities? For example, if I add first 2, if I add first 2, what do I get? I'll be getting 0.32. Then if I add the next 2 as separate block, I'll be getting 0.13. Whether these are equally probable? No, 0.32 is far away from 0.13. So these are not equally probable. So what we are going to do is that we are going to subdivide this into two. One is having 0.2 as it is, 0.2, and combine the remaining 3. So when I combine the remaining 3, I get 0.25, and for this x3 it is 0.2. So when I compare these two, these are equally probable for this problem. So we can write in stage 2 as, for this as 0, for x3 as 0, and for x4 as the remaining ones. Since in B2 this is your upper half and these all are your lower halves. So assigning 0 to the upper half and 1 to the lower halves. Okay, so this is how do we do in stage 2. Shall we go for stage 3? In stage 3 till stage 2 will remain as it is. So it will remain as it is. Will remain as it is. Okay. It will remain as it is. So what we are going to do in stage 3 is that, again, since this x1 is over, x2 is over, x3 is over, we will further subdivide this 0.12, 0.08 and 0.05. So again with an equal probability, if I add a 0.12 and 0.08, we get 0.20. We'll get, if I add these two in stage 3, we get 0.20. And if x6 is there, it will be having only 0.05, which are not equally probable. So whereas when we take this as separately, let me show. When we take 0.2 as separately and adding 0.08 and 0.05, 0.08 and 0.05, we get only 0.13, which is equally probable. Okay, 0.12 and 0.13 equally probable. So for this, assign 0 upper half and the lower half ones, which is stage 3. I'll show in stage 4. I think here, due to screenshot, you're unable to see this. I'll write it. Okay. So after the stage 3, comes our stage 4. But I'll show you. Stage 4. So what do we do in stage 4 is that we have already found out for x1, x2, x3, x4. Till this, it's over. Here you can see the stage 3, 0.13. So till this, we had completed in stage 3. So next, the remaining are only two messages, x5 and x6. So equally probable then. So by assigning 0 at the upper and 1 at the lower. Okay. So now check whether all the symbols are being completed. Yes. So from this tick mark, I can see that all the symbols are being equally assigned with a code. Okay. So what is that code? Is that for x1, see how many digits, what digits you wrote? You wrote that 00. So 00 is the code word. So for x2, it's 01. So mark as it is. For x3, it is, see the stage codes which we had assigned, zeros and ones, it is 1, 0. So write 1, 0. For x4, it is 1, 1, 0. So 1, 1, 0. For x5, 1, 1, 1, 0. So 111, 0 is the code word. And for x6, 1, 1, 1, 1, 4 ones. So this is your code word. So this is how to identify code words. So any doubts? Any doubts in identifying the code word? Because this is an important coding method. If you have any doubts, ask now itself. I'll give you some 2 or 3 minutes for asking doubts in any of this coding method. Because afterwards is all a simple mathematical calculation. This is what Shannon Fanon has been proposed for decoding messages. So any doubts till this in Shannon Fanon coding? The main objective is to find the code word. So code word can be found by using this method in Shannon Fanon algorithm. So if code word is found, remaining is all mathematical calculation that you are going to solve it. So any doubts? Yeah, when you are doing partition, the probability are exactly equal. The term equally probable is that it should be more or less equal. For example, if I write an equation 0.8 and a 0.2, if I compare that, whether they could be equally probable? 0.8 and 0.2 is not at all equally probable. The sense they are not nearly equal to each other. So whereas when we write 0.4, if you get in any problem 0.4 and 0.6 in any of our message probabilities, then they are equally probable. Okay, understood? In most of the cases, when you add all the probabilities, so ask the question from Tanuja, if you add all the probabilities, for example, in this case, add all the probabilities and check whether the probability of occurrence of all these messages is less than or equal to 1. It will be obviously less than or equal to 1 only, because our maximum efficiency or the information rate is not greater than or equal to 1. Not greater than or equal to 1. So when you add 0.3 plus 0.25, 0.2, 0.12, 0.08, 0.05, obviously you'll get 1 as your value. So the source coding theorem states that it is not greater than or equal to 1. Only for that this Shannon Fanon coding is applicable. Then only we can decode the symbols. If you add all this, you will get all the probabilities, you will be getting maximum 1. Okay, any other queries? If they are equal, in the case, for example, if I'm adding first three numbers, first three probabilities, if I'm getting 0.5, and the next 2 or 4 I'm getting 0.5. It is very well good. For the first division, it is 0.5. For the remaining division or the block, if I get 0.5, it is very well good. They are equally probable. So in this case, it is more or less equally probable. Okay. Shall we proceed for the next? How to find n value, average? Any doubts in this? Shannon Fanon decoding. So this is the methodology. Okay, I understood that. Okay, we'll go for the next. Next is finding the number of bits, which is an task for each of us. Okay, so I'm tabulating the same information that we have done till stage 1, 2, 3, 4. Stage 1, 2, 3, 4. I'll show this. Interesting. I'll finding the number of bits is the task. So how do I find the number of bits? Is that we are write the symbols, all the 6 symbols, x1, 2, 3, 4, 5, 6. Write its probabilities, the stage 1, stage 2, stage 3, stage 4, until code word. So which we had obtained. So we had obtained code word for x1, x2, x3, x4, x5, and xx. Count the number of bits in that. Just count the number of bits. So here there are 0, 0, so 2 bits. Here 0, 1, 2 bits, 1, 0, 2 bits, 1, 1, 0, 3 bits, triple 1, 0, so 4 bits. Here 4 ones, 4 bits. So this is how to find the number of bits per message. For x1, 2 bits. For x2, 2 bits. x3, 2 bits. x4, 3 bits. x5, 4 bits. x6, 4 bits. I think this is easier for everyone to find the number of bits. Next is to find the average. Average number of bits n bar. Okay, so summation k is equal to 0 to L minus 1 pk nk. So what you have to do is that see the probability. So probability of x1 is 0.3 into number of bits nk, which is 2. So 0.3 into 2 plus the second probability. Second probability is 0.25, number of bits 2. So 0.25 into 2. Third one 0.2 into 2. Third one, sorry, fourth one 0.12 into 3. Fifth one 0.08 into 4. Sixth one 0.05 into 4. So check whether all are there. 0.02 into 4, 0.12 into 3, 0.08 into 4, plus 0.05 into 4. So on summation of all these things, simple mathematical, you will get 2.38. So check whether you're getting this. Obviously, you'll get, if you're having calculator now, try this quickly. You'll get this, obviously. So 2.38. Okay. So next is we need to find code efficiency and redundancy. So how to find code efficiency? Simple formula. Code efficiency is equal to h by n bar. This h is entropy. N is your average number of bits. So I think now just now we had calculated average number of bits. I'll recall that. N is 2.38. N is equal to 2.38. And before the Shannon-Fanon coding, we had found the h value. H value 2.3568 bits per message. So h is equal to 2.3568. Take that value and take this n value 2.38. Substitute in the formula, we get 0.99. So this is your code efficiency. In terms of percentage, into 100. So you get 99% for this problem. 99 is the code efficiency in terms of percentages. So if I want to find redundancy of this code, 1 minus efficiency. So 1 minus 0.99, which we have got, which is 0.01. So this states that this messages will give you or will give us 0.01 percentage of error redundancy, or we can say that the code efficiency of this problem is 99 percentage. So any doubts in this? I think the ultimate aim in determining that this problem is obtained. We have found, when make a check with the question also, when make a check with the question, we have found entropy h, we have found out average length n, we have found code efficiency, we have found redundancy. I'll give you 2 or 3 minutes for calculating this. If you are having calculator, calculate, check it out. Because if you had understood this Shannon coding, then only it will be easier for you to understand Huffman coding. So I'll keep a preview on how this Shannon coding is being done. This slide I'll leave you for 2 or 3 minutes. Kindly go through this stage 1, stage 2, stage 3, and stage 4. After visualizing this, we'll go for Huffman coding in 2 or 3 minutes. If you're having any doubts, you can put in the chat box relevant to Shannon coding. Shall we proceed for the next topic? Any doubts in this? Okay, thank you, Pawan. If you had understood the Shannon coding, then Huffman is very much easier. Okay, just a slight bit change in the method of finding code words. Only that is the difference. The difference between the Shannon and the Huffman is obtaining the code words. Remaining all is the same. Okay, I'll drag this box. Now we are going to see okay, just using Huffman coding. Okay. Difference between the Shannon phenomena and the Huffman is that obtaining the code words. Remaining all the calculation of entropy, calculation of code efficiency, calculation of code redundancy is all same. Difference is getting the code words. Okay. So the first point in obtaining this is that the probabilities, the messages having probabilities should be placed in decreasing order as you have done same in Shannon Fano coding. So that remains same. Messages should be arranged in the occurrence of their decreasing probability. That is your descending order. Then the two messages of lowest probabilities should be assigned binary 0 and 1. Messages having lowest probability should be assigned binary 0 and 1. And two lowest probabilities in stage 1 are added and placed in stage 2. Again with probabilities in descending order. I'll show you this in in the same problem. How do we do that? Then you will understand it better. And we should repeat the same step until all the probabilities are being assigned with binary digits zeros and ones are completed. Till that we should do this same process. Two lowest probabilities in stage 1, adding them and placing in the next stage. And after the that stage, placing it in the next stage, and it goes on. So this is your Huffman coding method to obtain code words. So we'll see the same problem. Don't worry. Is stage 1 visible? Stage 1 visible for all? Anybody can unmute? I hope you all are able to see this stage 1. Is this visible? Okay. So first thing is that arrange the in descending order. Now, with respect to a question, most probably all the questions or all the problems will come in descending order. If not, also you should check the messages probabilities and arrange it in descending order. Okay, descending order is that maximum occurrence of probability message should be at the first and the minimum should be at the last. So this is your stage 1. So according to the Huffman coding, assigning values to the lowest probabilities. So see in this, where is the lowest probability? So the lowest probability occurs at x5 and x6. So for this x5 assign lowest probability is 0 and for this assign 1. So this is your stage 1. Okay, so this is your first step in stage 1. So remaining you leave as it is. Okay, so we'll go for the stage 2, then you'll understand it in better way. Okay, in stage 2 we had already assigned for x5 as 0 and 1. So when you combine these two, what do we get value? When you add these two probabilities, we get value 0.13. Okay, so in stage 2 we'll get already the values are present 0.3, 0.25, 0.2, 0.12 and 0.13. So you should not write as it is. 0 point should not be written as it is here. We should not write as it is. Okay, why? Because when you write like that, After 0.3, 0.25, 0.2, 0.12 and 0.13, that will not be in decreasing probability. So we should write in decreasing order in stage 2. So this moves to the top, which I am highlighting it in red, moves to the top. And this 0.12 comes to the bottom in decreasing probability. So here 0.3, 0.25, 0.2, 0.13, 0.12 is in stage 2. So any doubts in this stage 2? Combining the lowest two probabilities and rearranging it in decreasing order in the next stage. Okay. So I am proceeding for stage 3. Okay. So in stage 3, okay, in stage 2, I forgot to say one more thing. Okay. So this is being rearranged in stage 2 at last. So see in this, which are the two lowest probabilities? So this 2 will become your, I'll highlight with another color. So in stage 2, the two lowest probabilities are these two, 0.13 and 0.12. So for this thing, you assign 0 at the top and 1 at the bottom. 0 and 1 is being assigned in stage 2. So when you add these two, we get 0.25, 0.25, two lowest probabilities. So in the next stage, how do I write this 0.25? Is that in this fashion. Okay. When you add these two, I get 0.25. So in the next stage, I should write it in decreasing probabilities. So 0.3 will be as it is, 0.25 will be as it is. And since it is being arising from the bottom, keep it at the bottom itself. You can write at the top also, but always try to keep, since it is arising from the lowest probabilities, keep it in the lower level itself. Okay. Then this 0.25 which are obtained will go here, and this 0.2 will come down. So check whether these are in decreasing probabilities. So 0.3, 0.25, 0.25, 0.2. Yes, correct. These are in decreasing order. I have checked it. So now what we are going to do in this stage 3 is that combine the lowest two probabilities again, which is these two, which are these two. When I combine, I'll be getting 0.45. Yeah, I get 0.45. And assign, okay, I'll take another color, yellow. I'll take 0.45. So I am assigning 0 to the upper and 1 to the lower. Okay. So this is what happens in stage 3. So in next stage, I need to pass on these values to the next. So let us see what happens in the next stage. So I had combined, here it should be 1. I had combined in stage 3 0.25 and 0.2, which gives the probability value of 0.45. So straight away it goes at the top. Then the remaining 0.3 as it is, 0.25 as it is. So arranging it in decreasing probabilities. So now see which are the two lowest probabilities. These two. So these two are your lowest probabilities. So okay, I'll take another color for this. So these two, lowest two probabilities, 0.3 and 0.25. So which is in stage 4. So I'll get 0.55. 0.55. So this 0.55 should be passed on to the next stage with the probability of 0.45. So where does it goes? And I forgot. Okay, we'll write assign. I'll assign binary codes 0 for this and 1 for this. 0, 1 is assigned for this. Next in stage 5, 0, 1 is being assigned, so it goes 0.5 goes to the top. This 0.45 comes here. So assign for these two also 0, 1. And further is not at all required, since when you add these two, we'll be getting value 1. So after 1, we cannot, if we get only a single digit, we cannot assign binary zeros and ones. So until we get this value, this type of stages, we can stop the iteration. Until we get two symbols or two messages with zeros and one assigning, till that we need to solve it. After this, we need to stop this iteration or assigning zeros and ones. So if you do further, we'll get only one message. For that, we cannot assign any value, since our Huffman coding is using a binary formats. Okay, so I can stop till this. So any doubts till this? I'll keep till here. Any doubts? If you have, you can ask. Any doubts in Huffman decoding? Okay. Now, the next challenge is to find the code words. Find the code words is a big challenge. So I'll keep the stage 5 as it is, and I'll tell you for each and every message with its probability what is the code word. So kindly listen this. I'll take a blue. I'll take a blue and I'll highlight for 0.3 what is the code word. Okay, so see the message 0.3 on the stage 1, 2, 3, 4, 5. So where it has been assigned with an binary 0 or 1. So what are the places? In stage 1 not assigned, stage 2 not assigned, stage 3 not assigned, in stage 4 it is assigned with 0. See here, this is your tracking. So 0.3 in stage 4 it is 0, and this is being combined to give another value at here. Here. Okay, so here for 0.3 it is 0, and since it is combined with that, now to obtain another code called 0. So I can write the code word it in code word as 0, 0. Okay, you should write in reverse. You should see from the last stage onwards. This 0 should be first, then this 0 should be next. So this is your code word. This we call it as bit tracing or bit tracking. Any doubts in 0.3? Code word for 0.3? Okay. I'll go for 0.25. So see in stage 1, 0.25, nothing assigned, 2, nothing assigned, 3, nothing assigned. But in stage 4, it is assigned with 1. Then trace this where it leads to. So when we combine with this, it gives a value of 0. So trace this. So when I trace it, the bit tracing gives us for 0.25 like this. So 0.25, see from stage 5 bit tracing 0, 1. So 0, 1 is for x2. Understood this? Any doubts? Okay. Next, we had completed these two. Now I'll take another color such that you can differentiate them. I'll take yellow color. So next is 0.2. For 0.2 C, in stage 1 nothing is there. In stage 2 nothing you had assigned. In stage 3 we had assigned 0. Okay, so see the trace for this. So here in stage 3 it is assigned 0 and it goes to 0.45. So where nothing is assigned in stage 4 in 0.45. But this is being assigned 1. Sorry, it should be 1 here. I'll recorrect this. Is 0, 1. This is 1. Okay. For 0.2, nothing is assigned in stage 1, nothing is assigned in stage 2, but in stage 3 we had assigned it as 1. So when we combine and see in stage 4, nothing is assigned in stage 4, but in stage 5 when you see it is assigned with 1. So the trace period for this is for 0.2 is this bits. So we can write 1 of stage 5 and 1 in stage 3, which is 1 1. Okay, so then coming to the next 0.12, I'll highlight that in green. Okay, 0.12 in stage 1 nothing is assigned, we haven't assigned anything, but in stage 2 we had assigned 1. See this? So when we combine and it goes on to stage 3, there it is assigned with 0. So this is your trace, this is your trace. And see that if you combine this 0.25 and 0.2, we get 0.45 in stage 4, but nothing is assigned in this. In stage 4, for 0.45, nothing is assigned, but in stage 5, it is assigned with 1. So go to that 0.45 in stage 5. Okay. So this is your trace for 0.12. You can write 1, which is obtained from stage 5, 0, which is obtained in stage 3, and this one in stage 2. So this is your code word for S4, sorry, X4. Any doubts? So now what color to choose? The black I'll choose. For X5, which is 0.08. So in stage 1 itself, we had seen 0, and this when we combine goes to 0.13 in stage 2, and when it combines goes to 0.25 in stage 3, but in stage 4 it is not assigned. Okay, it is not assigned. Then when you combine that 0.45, it goes to 0.1 in stage 5. So this is your trace period of that, sorry, trace bits of that. So writing for 0.45 here we had assigned 1, so 1, remaining all in stage 4 nothing, in stage 3 0, in stage 2 0, in stage 1 0, 1 0 0 0. So this is your code word for X5 having probability 0.08. And the last message that you are having is 0.05. I hope only 6 colors are available, so I'll take the white color. Probably it may be shown, I think so. So here in X5 we had assigned it to be as 1. In white, white is visible. Ah yes, at least something it is visible in white. So 1, One is in stage 1, and when you combine it goes with along this trace period. In stage 2 it is 0.13, we are having 0, and in stage 3 it is 0.250, and in stage 4 you don't have, and it goes to stage 5 0.45. So this is your bit tracing for 0.05. So when you write code word stage 5 1, stage 3 0, stage 2 0, and stage 1 1, they were obtained for all the 6 messages. For all the 6 messages we have got equivalent code words. Now it is easier for you to find the number of digits. So 2 digits 2, I'm taking it here. 2 digits, 2 digits, 2 digits, 3 digits, 4 digits, 4 digits. So this is how to obtain Huffman codes. So any doubts in this? Any doubts? If you're having any doubts in this, Huffman code, any doubts in Huffman codes, you can unmute and ask. The only thing is that the tracing of bits should be done carefully. Remaining all combination and all, you all are familiar with that, how to combine the lowest probabilities and arranging it in descending order in the next sequences or in the next stages is easier. The bit tracing plays a major role. If you trace the bits correctly, your code word is correct. So after writing the code words, determine the number of digits. Then we can easily find the average number of bits. Average number of bits by the formula messages, probability messages 0.3, code words, code words number of bit is 2, for 0.25 it is 2, for 0.2 it is 2, for 0.12 is 3, 0.08 it is 4, 0.05 it is 4. So when we manipulate we get 2.38. This is to find n, and easily we can find efficiency. N is here itself, h is what we had found before the Shannon-Fredon coding, the same problem we had taken. So entropy will not change. So entropy is here, we get 99% in terms of code efficiency in percentages. Then redundancy is 1 minus code efficiency, we get 0.01. Again, I'll put this slide for computation of Huffman codes. So any doubts in this you can ask. I'll give you 2 or 3 minutes for viewing this. Any doubts you can ask either by unmuting or put it in the chat box. Because Shannon-Fredon coding and Huffman coding are the basic coding methods which are used in information theory. Without knowing these two codes, okay. Without knowing the procedure for solving Shannon-Fredon coding and Huffman coding, we cannot go into any other concepts of any other issues. We cannot solve Shannon-Fredon or the source coding theorem at all. Cannot do it. So any doubts? If you have, you ask now itself. Any doubts in this? So this I had shown you in the last class also, that what we are going to see in next class, last Wednesday. So information and entropy topic, properties of entropy and average word length with relevant examples. So we have taken Shannon coding theorem. Okay, Shannon coding theorem. So the same formula with a different notation of properties, average word length, entropy, entropy and average word length, and this is the source coding theorem that we have done. Okay, so these are the reference